Hello everyone, my name is Pedro Miranda Pinheiro. I'm a graduate student at Universidade Federal do Rio Grande, and I'll be presenting a work titled A Novel Concept for Hybrid Unmanned Aerial Underwater Vehicles Focused on Aquatic Performance. This work was done by Alexandre Horn from Instituto Federal de Educação, Ciência e Tecnologia Sul-Rio-Grandense, myself, Ricardo Grando from Universidade Federal do Rio Grande, César da Silva from Universidade Estadual de Campinas, Professor Armando Neto from Universidade Federal de Minas Gerais, and Professor Paulo Drills from Universidade Federal do Rio Grande. I'll start now with a brief introduction. Hybrid unmanned aerial underwater vehicles are systems that can navigate in air and underwater and do not require change in geometry to perform transition. This means that they combine the characteristics of unmanned aerial vehicles and unmanned underwater vehicles. And they have a great challenge, which is to deal with two really different specific masses for each media. Our motivation here is that many applications require trends in both media for full perception, uh, such as search and rescue, environmental research, and inspection of partially submerged structures. So these vehicles are really needed, but the current state of the art penalizes motion efficiency in favor of simplicity and ease of control. So our problem in this work was to design a new concept of a hybrid vehicle that focuses on both aerial and underwater performance. Now I'll show you some of the related works. On the left, we have the first concept of modern HUAUV, which was proposed by Drills et al. From 2014. On the right, we have the first transmedia-focused concept, which was proposed by Ma et al. From 2018. And both of them have 4 aerial propellers and 4 underwater propellers. The second one has also 2 frames. Now I'll show you 2 of the most recent proof of concept prototypes. On the left, we have the Navigator, which has 8 coaxial aerial propellers. And the second one on the right is the Loomcopter, which has 4 aerial propellers plus a ballast, which is a system that fills with water in order to control the buoyancy. Both of them need to turn 9 degrees to move forward, which is not a good thing because you have a larger drag force on the vehicle. And the last one is a 4 aerial propeller with fixed wings and a bladder for underwater glider motion. It is a concept that combines UAV with underwater glider and is really different from the others. So you may notice that none of these concepts has forward-facing propellers. And this is a great issue because they have high drag force due to large area normal to the vehicle motion. Now I'll show you our methodology. This is the hydrone system design. Is our proposed concept. It has one set of coaxial air underwater propellers and a second set which is perpendicular aerial underwater propellers. Since it has forward-facing propellers, it has a lower drag, but it has no roll angle control underwater, relying only on static stability and moving like an Ackermann vehicle. It also has a positive buoyancy. This is our dynamic model. It has some specificities, which I'll show you now. Some of them is the mass plus added mass term, the translational drag coefficient term, the net weight, which is due to buoyancy, the switched actuator forces term, which is due to two separate systems, one for the air, one for the water. The inertia tensor plus added inertia term, the rotational drag coefficient term, the rotational static stability term, and the switched actuator moments term. Now, this is our z-axis control. You may notice that we only have two actuators for the z-axis control underwater. This is our attitude control, where you may notice that we have no roll angle control. This is the aerial y and x-axis control, which is done by changing the roll and pitch angle. And this is the underwater nonlinear control law. Now for our experiments, this is our used simulation used parameters. You may notice that our vehicle has a positive buoyancy here, and it also has a 2 centimeters between the center of mass and the center of buoyancy, which is done by to improve our static stability. These are the propeller parameters. You may notice that we have two sets of parameters for aerial propellers, and this is because some of the concepts used in a comparison that I'll show you later, they use aerial propellers underwater. I'll show you first our waypoint navigation simulation. Our vehicle motion is like a classic UAV on the air, and underwater is able to navigate with the two forward-facing propellers. It gives a higher speed, lower drag, and you may also notice that we have the switched actuator on the bottom right corner. Okay, now I'll show you our comparative analysis. The vehicles had to track this reference trajectory, and you may notice that Hydrone was performed really well in this, while the other three concepts were pretty similar. Only HUAUVs et al. From 2018 had some trouble with the z-axis, and this is due to the ballast system, which has to fill with water and it takes time. And for the comparative analysis, we had this energy equation, and you may notice that our vehicle was able in the same time as the others, it was able to move in for 51 meters, and it also has a great energy distance ratio, which is really good comparing with the others. And this is mainly due to the aquatic specialized propellers and the lower drag forces. So our conclusions and future work, our proposed concept, Hydrone, maintains aerial quadrilateral performance. It has better hydrodynamics than the current state of the art. So it has a higher underwater energy efficiency. And it relies on static stability and non-holonomic kinematics. For our future work, we'd like to build and evaluate a prototype in real-world applications. We are currently working a lot on this. Uh, and we will also design a robust control strategy to guarantee the stability under disturbances. Uh, if any of you has some questions, you may ask me right now on Zoom or email me. Thank you very much. I would like also to thanks CAPES and CNPq and also PRH from ANP. Thank you very much.